So welcome, day number 2. We're going to be jumping into module number 2 today. Module number 2 is our EIGRP implementation. We talked a little bit about this yesterday. EIGRP is an advanced distance vector routing protocol. And it's considered to be advanced because of, so a lot of the characteristics that it takes from link state. Probably some of the primary differences are from a traditional distance vector routing protocol is that it doesn't do periodic updates. It only does incremental updates. And we'll get into the differences and so on with EIGRP as compared to other traditional legacy distance vector routing protocols. We'll talk about some of the enhancements that EIGRP brings. We're going to go through 5 different lessons in this particular module. We're going to talk about how EIGRP routers form their neighbor relationships. What is the process that they go through to establish that neighbor relationship? What are some of the requirements for routers to become neighbors? And we'll talk about, all of the unique characteristics of EIGRP in how it establishes those neighbor relationships. And obviously, we're also going to go through the process of identifying not only those unique characteristics, but how do we troubleshoot that? How do we make sure that we're monitoring that correctly and so on? We will talk about EIGRP for both IPv4 and IPv6 in this particular case. The configuration is slightly different between the two, but as far as the troubleshooting goes, as far as the theory of EIGRP, successor, feasible successor, feasibility condition, all these things that we're going to talk about, all of those concepts are the same between both EIGRP for IPv4 and IPv6. So we'll talk about that. We'll take a look at the metric that EIGRP uses and how it decides what path it's going to take through the network. EIGRP uses a composite metric that has different K values, what we call metric weights, that go into the calculation of the metric itself, which includes components like bandwidth and delay and reliability and load and so on. And then we're going to get into optimization of EIGRP. That's our third lesson, where we're going to talk about stub routing features, route summarization, load balancing features, and so on. Pretty important topic for a couple of reasons. Number one, it allows us to increase the scalability of the protocol. But number two, and more importantly, there is a lab on the exam regarding that particular topic, stub routing, specifically with EIGRP. So obviously that's going to be an important topic for you guys if you're going on to take the test a little bit later on. Then we're going to get into basic EIGRP for IPv6. So we'll take a look at all of the concepts that we talk about with IPv4, and we'll apply those concepts in IPv6. And then finally, we'll wrap up the day, most likely, and we'll wrap up the module number 2, by talking about how do we do EIGRP named configurations, where we actually take all of the classic EIGRP configurations and we combine them together into a concise configuration option called EIGRP named configuration. So we're going to take a look at a lot of different things in this case, and it's all great stuff, right? We're going to spend quite a bit of time talking about all this stuff. So that's what our goal is for today, all right? Maybe hopefully we can even get into a little bit of OSPF today, but that's going to be a pretty aggressive approach, but we'll see what we can do, all right? So let's go ahead and jump right into lesson number 1, which is establishing EIGRP neighbor relationships. We know that EIGRP is an enhancement to IGRP. Probably the biggest difference, actually the biggest difference between EIGRP and IGRP was the fact that IGRP, the Interior Gateway Routing Protocol, which was actually the very first IGP protocol that existed, was developed as a classful routing protocol, whereas EIGRP is a classless routing protocol, meaning that it supports subnetting, summarization, etc. As far as the protocol itself, it's a very efficient routing protocol. It does partial updates. It does incremental updates, meaning that it doesn't send out periodic updates. We also know that it uses multicast to disseminate information. But the first step, of course, in any dynamic routing protocol relationship, with the exception of RIP, is to go ahead and establish adjacencies. And find a way to establish neighbor relationships between these routers before we can exchange any routing information and before we can converge. So we're going to talk in this particular first lesson about what are the basic features of EIGRP, stuff that you would have learned in a CCNA class, but again, we assume that we're kind of starting all over again in this particular case, and we're going to introduce a lot of these concepts in this particular lesson. We'll talk about how EIGRP ensures reliable transport, which is an important concept because EIGRP sits right on top of IP. It doesn't have, it doesn't utilize a lot of the features that application layer protocols that run on top of TCP might have. So the concept of sequencing, acknowledgements, and so on, that's built into the protocol itself. And we'll talk about that. We'll talk about how we add routes to the routing table. What is the process, right? It's establish the neighbor adjacencies, then exchange all of our routes to build our topology database, and then run Dijkstra's, I keep saying that, I don't know why, run the dual algorithm against that database, and then extract the best routes based on the algorithm that EIGRP uses, that diffuse update algorithm. We'll take a look at the timers, specifically the hello and the dead timers that EIGRP uses. And then we're going to take a look at how EIGRP adjacencies are going to be formed over different network types. What do I have to do if I want to establish EIGRP adjacencies over frame relay? What do I have to do if I want to establish them over a layer 3 MPLS VPN or over a layer 2 MPLS VPN? All right, so let's get started on just learning again all about EIGRP and its features and functionality. All right, now we know that EIGRP is an advanced distance vector routing protocol. Yesterday we talked about the concept of distance vector versus link state, but EIGRP is often considered to be a hybrid protocol. It's a little bit of a misnomer because technically EIGRP is a distance vector protocol. Fundamentally, it does routing by rumor. It only exchanges information about distance and vectors for destinations. So it doesn't take characteristics of link state from that perspective. But it does incorporate a lot of the features that you might see in a link state protocol. It has high quick convergence capabilities. In fact, EIGRP, if it's configured correctly, can actually converge even faster than OSPF. It does partial and bounded updates, which means it only sends out updates when they're necessary, and it only sends those updates to individuals that need to hear that information. We use a very sophisticated metric. It's probably one of the most sophisticated metrics outside of the BGP route path selection process. The EIGRP process is routing process and metric process is probably one of the more complex ones that you'll see. We'll break it down in this chapter. We'll break down how that metric works and how you can evaluate that metric and manipulate it and so on. It has support for variable length subnet masking, which is fine. I mean, it simply means it's a classless routing protocol. It can operate classfully using the auto summary option, but we try to avoid doing that as much as possible. And we simply use the variable length option. And the nice thing about EIGRP is it supports multiple network layer protocols. It's built in. In fact, because the way EIGRP carries information in TLVs, what we call these type-linked value fields, which are generic containers that allow me to carry information about routes and other types of information about the datagrams that I'm trying to process. EIGRP natively supports different protocol stacks, IPv4, IPv6, even IPX if it was necessary at some point or another. All right. In addition, EIGRP also supports seamless connectivity across the data link layer. So we can run EIGRP over frame relay, over Ethernet, over PPP, HDLC, and so on. These are all very important components of the protocol. There's two things that you basically have to learn when you're learning protocols. Number one, obviously you need to learn how to implement it and troubleshoot it. And that's the simple piece, because it's just really a basic configuration. There's obviously some enhanced or some advanced features that you can add, which includes some additional configuration features which you guys may or may not be familiar with, but overall the configuration is relatively simple. Troubleshooting, also relatively simple. I mean, there's only so many commands that you can use to troubleshoot the relationship, neighbor relationship, show IP EIGRP neighbors, maybe a detailed option, maybe take a look at show IP EIGRP packets, and there's some other basic ones that we'll take a look at. But overall, troubleshooting neighbor relationships is relatively simple. Understanding the topology database is relatively simple. So the configuration and troubleshooting is not too complicated. But what's more important, I think, in dealing with these protocols is understanding fundamentally how these protocols work, right? What is it that EIGRP does with information? How does it calculate these databases? And that has to do a lot with understanding the theory of the protocol, but also from an engineering standpoint, understanding the impact of changing specific components about that protocol that would change how the protocol behaves, right? One of the things that I harp on in my classes is I want to make sure that everybody understands the algorithm that's tied with the protocol, right? And in our particular case, that algorithm is the diffuse update algorithm, and we'll talk about that. So fast convergence, like I said, it can be natively fast, but there are things and steps that you can take to make it faster. We use like a very sophisticated metric. It's a 32-bit format, a 32-bit metric. We call this a wide metric, as opposed to what IGRP used, which wasn't a 32-bit metric. Again, we'll talk about all of these different types of things that we can do to implement EIGRP and so on. Now, as a protocol, EIGRP sits right on top of IP. This slide is a little bit confusing because it references TCP and UDP in the slide, but that is only there simply as an example of other protocol types that exist based on information that's encapsulated inside of IP. So EIGRP runs directly above IP. There is no transport, quote-unquote, transport layer component. It is protocol number 88. OSPF, incidentally, is protocol 89. And it uses something called the Reliable Transport Protocol for guaranteed delivery of datagrams, ordered packet delivery, etc. Now let me talk about that for a second, because I saw this as well in one of my discussion groups that I'm a member of. People were discussing, again, it was related to the same the same discussion regarding whether or not EIGRP runs on top of the transport layer. Is it a transport layer protocol, and so on. And somebody mentioned in that discussion, well, EIGRP uses another transport layer protocol called RTP for reliable delivery. And I said, well, wait a minute. there is no transport layer protocol called RTP. And that's actually true. RTP, even though all the books and everything you read, they seem to suggest that there is a secondary protocol that gets incorporated into the use of EIGRP. So somehow you would do a Wireshark capture on some EIGRP transactions, and you'd see the EIGRP datagrams going back and forth, but then you'd also see these RTP segments going back and forth, and that's simply not true. All right. Even though it's called the Reliable Transport Protocol, it's actually integrated into EIGRP. So there's not actually a spawning of a secondary protocol from EIGRP. RTP provides things like sequencing, acknowledgement numbers, and it's, you know, it's those sequence numbers, those acknowledgement numbers are carried inside of EIGRP. In fact, let me pull up the header for EIGRP. So what I've got here is I've got what we, well, essentially the EIGRP packet header. And you can see that the header itself has the sequence numbers and the acknowledgement numbers built in. And this is what I'm talking about when I say that RTP, the Reliable Transport Protocol, guarantees ordered delivery and guarantees you know, that the packets were delivered. Well, acknowledgements are how we do that, right? I send you an update, you send me an acknowledgement that you received the update. I send you packets or datagrams with sequence numbers, which guarantees or ensures ordered packet delivery. So even though they classify RTP as a separate function, it's really actually built into the EIGRP header, and that's where the reliability comes in. All right. Version obviously is going to allow us to identify the version of EIGRP opcode, which is the operational code. That's going to allow us to identify the different packet types. So an update is an opcode of 1, a query is an opcode of 3, a reply is an opcode of 4, a hello is an opcode of 5. Acknowledgements are also an opcode of 5 as well. It's not listed here. So we can identify in this field what type of EIGRP message it is. A checksum verifies the integrity, of course, of the EIGRP data. We have various flags that can identify different functions within EIGRP. And then we have this autonomous system number, which is a 32-bit number that allows us to identify the domain that EIGRP is running in, okay? And that's a value that you set from 0 to 65,535, which gives us the opportunity to establish the EIGRP autonomous system. Everything else is carried in these things called TLVs, type length value fields. Type is a type code, which allows us to identify what type of message it is. Length is how large the field is, and the value is the actual payload, which contains the information that I'm trying to transport. So TLVs are like generic containers, and lots of protocols use TLVs to allow us to essentially identify how data is carried through the network, right? It's a generic description. I'm trying to think of probably the best way to describe it. I mean, you're going to see the references to type, length, and value in lots and lots of different scenarios, lots of different programming scenarios, and so on. So again, it's just an encoding scheme, and it's a generic encoding scheme that allows us to carry elements within a particular protocol. Type is usually some sort of binary code. It could be alphanumeric. It could be represented as a hexadecimal value. And that just indicates, like I said, what is the field that is part of that message? What kind of information am I carrying? The length is the size of the value. That's usually going to be listed in some sort of bytes. and then the value field is just a variable sized field that contains the data portion of the particular message. So in this particular case, the TLVs are being carried inside of EIGRP. It's used in programming languages, it's used in ISIS, it's used in LLDP, the Link Layer Discovery Protocol, it's used in Radius. I mean, there's just all kinds of places that you're going to see these TLVs that are used based on these different protocols. It's even used in things like SMTP, FTP, POP3, SIP, all kinds of places. So lots and lots of uses for these type length value fields. But this is essentially what makes EIGRP so portable to other protocols, because we can actually just simply change the values, those TLV values, to carry anything we want inside of EIGRP. Now, the header itself is going to be contained in every EIGRP packet. There isn't a whole lot to the header, as you can see here. It's a pretty basic header. So really the meat of what we're trying to accomplish is carried inside of these TLVs, inside the EIGRP message. EIGRP supports both unicast and multicast. There are certain scenarios where multicast is going to be used, 224.0.0.10, or if it's for IPv6, FF02:A, that's part of the process, right? Only specific packet types are sent reliably, meaning that there's only specific packet types that actually require an acknowledgement. Those packet types include the update, the query, and the reply. Again, there's 5 message types that we talk about with the EIGRP: hello, update, query, reply, and acknowledgement. We're not going to acknowledge acknowledgements, obviously, and hello packets don't get acknowledged. They're sent unreliably because we simply get hello packets back. All right. Now, they do mention, of course, on the slide here, RTP sends packets, EIGRP packets reliably, and the Reliable Transport Protocol sends these multicast packets quickly. But again, like I said, it's really just an EIGRP packet. In the end, that's what we're referencing here. It's just simply an EIGRP packet. All right. So the process for establishing neighbors and exchanging routing information and converging in the network is fairly simple. The routers themselves have EIGRP enabled on them. That means they're going to start sending out periodic hellos. These hello packets are sent every 5 seconds on high-speed links, like anything that's above a T1 type speed, 1.544 megabits per second. And then every 60 seconds on slow-speed links. And we'll talk about the timers and how we can manipulate those timers a little bit later on. All right. The dead timer in EIGRP is 3 times the hello timer. So let's talk about that for a second. A dead timer is essentially how long I'm going to wait before I decide that a neighbor doesn't exist anymore. So let's say that we establish a neighbor adjacency, R1 and R2 become neighbors because they've exchanged hellos, they've identified that they're in the same autonomous system, and the various properties that have to match in order for these routers to form an adjacency exist. Well, I expect to get a hello every 5 seconds from you, all right? Assuming that I'm using the standard timer. If I don't get a hello after 10 seconds, okay, I missed a hello. But if I don't get a hello after 15 seconds, by default, I decide that you don't exist anymore, and I delete you from my neighbor table, and then I delete everything that I've learned from you from that process. Okay. Remember yesterday, guys, we talked about the 3 major things that you need to know about a routing protocol. Number 1, the messages. the routing protocol message types. Number 2, the data structures. And number 3, the algorithm. So you're kind of seeing 2 of those 3 things on this slide right here. Hello packets, updates, acknowledgements. The only thing you're not seeing here is a query and a reply. And we'll talk about when those queries and replies take place. But in normal transactions, you should not see queries or replies. They only occur in specific instances. And then we're also seeing the data structures. The neighbor table, which basically is a database that includes all of my adjacency information. So all of the routing information sources that I'm getting routing information from. The topology table, which includes everything that I'm learning in the process of routing. Not only the best route, the next best route, the third best route, the fourth best route, and so on. And then finally, the third data structure, which is my routing table. Well, guess what BGP has? A neighbor table, a topology table, and a routing table. Guess what OSPF has? A neighbor table, a topology table, and a routing table. So this is a very common concept in all of our routing protocols. All of our routing protocols kind of follow this logic. So it makes sense to say, well, I'm not going to start troubleshooting my routing table until I've identified that all the routes exist in my topology database. And of course, I'm not going to go in and try and troubleshoot my topology database if I don't have neighbors. All right. So as particularly for the troubleshooting test, think in those lines, well, let me make sure I have my neighbors first, because if I don't have neighbors, ain't nothing else going to happen, right? We're not going to be able to learn anything else in the process if I don't have my neighbors. So let's talk a little bit about some of the characteristics that have to match in order for EIGRP routers to actually form an adjacency. Number 1, they have to be in a common subnet. All right, they have to be in a common subnet. So you can't have a different subnet mask on router 1 and router 2. You'll actually identify, there'll be an issue in that configuration, and the routers won't form an adjacency. Number 2, if you're running routing protocol authentication, and we use MD5 authentication in the case of EIGRP, you need to make sure that the authentication parameters match between the 2 routers, obviously. You don't have to run authentication. We're not going to be doing that. We're going to be doing our first discovery in a minute here. So you don't have to be running authentication, but you could if you wanted to. All right, and we'll in module number 7, I believe it is, we'll talk about routing protocol authentication. Number 3, probably one of the more important ones, is that both routers have to be in the same autonomous system. Okay, they have to be in the same autonomous system. The autonomous system is not a registered AS like you might see with BGP, but it does have to be a common AS. So if the routers don't share a common autonomous system, they will not be able to form an adjacency. Additionally, the K values have to match between the 2 routers. The K values have to match. We'll talk about the K values a little bit more. Cisco recommends that you never change the K values. So there's really no reason why your K values shouldn't match. But yeah, your metric weights, which is what they're called in the configuration, those need to match. Those have to be the same. And we'll talk about, again, why I would change those potentially, even though Cisco says don't ever change them, and what the benefit would be of changing them, which there isn't a whole lot. So let's see, what else? You could have some issues if there's an MTU mismatch between the 2 router links as well. So you may want to make sure that the MTUs match on each side of the router as well. All right, we'll play around with that. We're going to jump into our first discovery for today, which is just basic configuration and investigation of EIGRP. And in this discovery, I'm just going to basically show you guys how I verify EIGRP operations, how I configure it. We'll do a little bit of backfill on some of the configuration elements that we're going to be configuring here, and then we'll get into talking about basic troubleshooting and so on, and then we'll continue on to some more advanced topics as part of our EIGRP discussion. We still have a lot to talk about. We still need to talk about the algorithm. We need to talk about the concept of a successor, a feasible successor. What is a feasibility condition? How can I manipulate routing information and so on? All right. So this is our topology that we're going to be using in this particular case. HQ already has EIGRP configured. We have 3 different links that we're seeing here. We have a point-to-point serial link between HQ and BR1. That's in the 172.16.1.0/30 subnet. We have a simulated Metro Ethernet link or a WAN link between HQ and BR2. That's a 172.16.2.0/30 subnet. And then we have a frame relay connection between HQ and BR3, 172.16.3.0/30. And we're going to be configuring EIGRP on each of the individual routers, BR1, BR2, and BR3, and just verifying adjacencies, verifying convergence. So we're seeing essentially 3 different topology types here. One is a point-to-point topology, one is an MBMA topology, and one is a broadcast topology. Just to kind of demonstrate the concept of how these routers communicate over these different data link layer topologies. All right, so let's start by just doing our basic EIGRP configuration on BR1. And I'll talk a little bit about this configuration and what it is that I can do to make sure that this configuration works correctly. Let's start by doing a quick investigation of what is configured on our HQ router. Let me start my routers again here. All right, now I'm going to do a couple of quick commands here. First thing I'm going to do is I'm going to do a show IP route connected, because I want to see all of my connected interfaces, make sure I understand which interfaces are running which subnets. So serial 2.1 is the 1.0 subnet, Ethernet 1.0 is the 2.0 subnet, serial 2.0 is the 3.0 subnet, and then I also have a loopback network that's simulating a local connection. All right. I'll also do a quick show run pipe section EIGRP just to check my EIGRP configuration. Now you'll notice here that there's a couple of different ways that you can implement the network statement. So let's talk about the network statement real quick, because that's an important concept. All right, so network statements, and this would effectively apply to OSPF as well. It doesn't apply to BGP because BGP doesn't use wildcards in its network statements, and the network statement in BGP is really kind of unique and different anyway in what it actually does and how it actually works. But we have the ability of providing these network statements in IPv4 to implement the protocol. So the network statement actually does 2 things. And these are distinctly different things that I want you guys to understand. Number 1, it instructs the router to enable the EIGRP, well, we'll just call it the routing protocol, on a particular interface. All right, that makes sense. If I want a routing protocol to run on an interface, I'm going to go ahead and include that network interface in the network statement so I can run the protocol. Well, if you look at our topology diagram here, you might look at this and go, well, really the only interfaces I need to run EIGRP on are the serial interfaces. Well, serial, Ethernet, and serial, because those are the only interfaces where I have other routers to talk to. And EIGRP is a protocol that is designed to allow me to communicate to other routers. All right, and that's very, very true. In the case of HQ, I definitely want to make sure that EIGRP is running on each of those 3 serial links, and we're communicating over those networks. Okay. So that is definitely one of the things that the network statement does. However, the network statement does something else that is really important. It instructs the router to advertise the networks included in the network statements. This is a different statement than the first statement. The first statement is just implementing the protocol on the interface. The second statement is what allows networks to be included in the EIGRP process. As an example here, if I don't include these loopback interfaces in the EIGRP process, they don't get advertised. There's no reason to run EIGRP on the loopback interfaces from the perspective of exchanging routes with other routers, because there are no other routers on those loopback networks. But if I don't include network statements, or I don't have network statements that include those subnets, then those networks do not get advertised. So that's a distinctly different thing than simply enabling the protocol on the interface. All right? What does a network statement not do? All right? Network statements do not define how networks are advertised. All right? And let me explain what I mean by that. Because you can enter network statements in many different ways. You can make them very generic, or you can make them very specific. And there's a common misconception that the way that you put in your network statements determines how routes get advertised in the EIGRP process. And that's just simply not true. Routes are advertised based on the actual configuration of the interfaces that are included in the routing process. So if I have a /30 on a serial link, even if I put in a generic 8-bit network statement, as long as that /30 serial link is included in that network statement, a /30 route will be advertised. All right? So it's actually the configuration on the interface itself that determines how the networks are advertised. Just think of a network statement as a light switch. You're turning on or turning off the protocol, and you know, the brighter the light, more generic the network statement, the more of the room is illuminated, or the more networks get advertised. All right? So people always ask me, well, what's the best choice then? Do I make my network statements more specific, or do I make my network statements more generic? And there are pros and cons to both, right? To me, the biggest con of making a network statement more generic is that it will include inevitably, or could include inevitably, a bunch of interfaces or networks either now or in the future that you may not want to include. Does that make sense? So if you make your network statements more specific, then you have the capability of controlling, more accurately controlling what networks are going to be included in the EIGRP process. All right?
Yeah, that makes sense. Like say you did a /16 statement, and then you create a /24 down the road. That in that same 16,
exactly,
area, it's going to be advertised, even though maybe you didn't want that.
Exactly. So in my opinion, I think a more specific network statement is probably more warranted, but it makes more work for you, obviously, depending on how many networks you have. The way that I like to do it is I like to do it based on what's actually configured on the interfaces themselves. and very rarely I might go beyond that. I might break away from that traditional configuration option because I might have just too many interfaces, and I don't want to restrict which interfaces can be participating in EIGRP, but it just depends. So let's say that I had there's two ways to enter network statements in EIGRP. You can use a wildcard. Well, use an inverse mask. It's not a wildcard mask per se. It's an inverse mask because it does have to be literally consecutive zeros followed by consecutive ones. Or you can use the no mask option. All right. This is what we call the classful option. So if I go into my router and I say network 172.16.10.0, and that's all I put, the router is going to change this to a 172.16.00 because it's going to assume that you're just using the class. So basically, in this particular case, without a wildcard mask or an inverse mask, it's going to assume that this is a Class B address, so all you care about are the first two octets. Now, if I did this, 0.0.0.255, now I'm using the inverse mask. Zeros in the inverse mask indicate that I care, and ones in the inverse mask indicate that I don't care. So in this particular case, 172.16.10 would be the only networks that would be running EIGRP and be included in the EIGRP process. This would be any interface that starts with 172.16.10. All right, and then the last octet is irrelevant in this particular case. So that's really your two options. You can choose to use classful network statements, or you can choose to use classless network statements with inverse masks. In the case of the mask, though, it does literally have to be an inverse mask. It cannot be a bitwise mask like you might see with like an access list where you can have all kinds of crazy combinations of bits, right? In an access list, you can have a mask of 1.240.12.63. That would be a valid wildcard mask in an access list. Wouldn't probably be used that often because it's way too specific for what you're trying to maybe accomplish, but in the case of a mask in network statements, they do have to literally be an inverse of a subnet mask, okay? So let's go back to our HQ router, and you can see here that it was implemented essentially both ways, right? We've got our wildcard mask here, our inverse mask, excuse me, which is an inverse of a /30, which is a 252. Try that again. Show run pipe section EIGRP. And so essentially this is how I would basically do it. I would actually come in here. This is probably one of the easiest ways. You just do a show IP route pipe include C, and you can grab all of your connected networks, and you can grab all the masks off those connected networks, and you can start to create your network statements based on that. This is a 192 address, so it's already assumed to be a /24, and it happens to be a /24 on the loopback, so there was no need to include a network statement in this particular, a inverse mask in this particular case. All right, now I could have done this a little bit differently. I could have done something like this, config T, no router EIGRP 100. All right, and I'll go ahead and re-add it, but this time I'm going to combine these three network statements into one, but still not make it so generic that essentially every 172.16 network would be included. So I would type router EIGRP 100, network 172.16 0.0, 0.0.3.255. So now in this particular case, this is going to be, and this is an easy way to remember this, guys, by the way. This is a block of 4 starting at 0. All right. Essentially, in a wildcard mask, you can have a .1, You can have a .3, a .7, a .15, a .31, a .63, a .127, and a .255. Those are the options that you're going to have. 1, 3, 7, 15, 31, 63, 127, 255. This is a block of 2. This is a block of 4. This is a block of 8. This is a block of 16. This is a block of 32, block of 64, block of 128, and a block of 256. So that's kind of an easy way to figure out what's included because it's a block of 4 starting at 0. That makes sense. Which would include network 0, 1, 2, and 3. So I did include 1, 2, and 3. In this case, I also included network 0, which is not a big deal because, again, unless network 0 exists on my router, it doesn't really affect. Because this does not define a route. We're not telling the router to advertise that route. We're just simply, it's a light switch where we're just simply turning on the protocol on interfaces that are included within that particular range. Does that make sense? So let me go ahead and add my 192. Now I could do 168.0.0, 0.0.0.255, but it's redundant. And in fact, if I do a demonstration here, it's redundant because it's already a /24, so it actually took out that wildcard mask because it's already a /24 anyway. All right. So they want us to go ahead and enable the process on BR1. So I'm going to go into BR1. Oops. What did I do with my BR1? Let me get that back. Hold on. I must have accidentally closed it. Oh, I see what happened. It jumped out of my window here. All right. So they want us to go ahead and configure EIGRP on BR1. Usually the first thing that I'm going to do on a router, just to make sure there's not going to be any conflict, is I'm going to do a show IP protocols, just to make sure that I'm not running any other routing protocol on the router. All right. And also I can see that I'm running IP routing, which is important as well, but that's by default. Routers run IP routing. So I'm going to do a quick show run pipe, show IP route, pipe include connected, and these are my two interfaces that I want to run EIGRP on. Config T, router EIGRP. Again, make sure that you select the same autonomous system number, and then I'm just going to put in my network statements based on what I see above. 16.1.0, 0.0.0.3, and then network, get my adjacency, network 192.168.1.0. Again, I don't need a network, I don't need an inverse mask in this case because it's already a /24. Okay. Now you do notice that we did get a syslog message. It's a level 5 neighbor change. And we saw that we established an adjacency on our serial 2.0. And that's, essentially it. Once you've identified you have an adjacency, everything else kind of happens automatically. All right. Which we may or may not want to happen. That's an important concept. And we'll talk about that later when we get into route manipulation and policy-based routing. Because neighbors basically by default exchange everything. The only exception to that is BGP. But BGP is kind of a weird monster anyway. It's a lot different than all the other routing protocols. All right. So let's go ahead and do BR2 now. And we'll do the same thing on BR2. I like to be consistent. Show IP protocols to see if I'm running any routing protocols. Show IP route pipe include connected. Config T, router EIGRP 100, network 172.16.2.0, 0.0.0.3. And I should get an adjacency there. And then also network 192.168, 2.0. And we're good to go. All right. We're going to do some other verifications in a little bit as well. We'll talk about what those verifications are. Now, I could have done something a little bit different in this case as well. I could have changed how I decided to do my network statements. Oops, what happened there? There we go. I could have decided to change how I did my network statements. There's an even more specific way that you can actually do your network statements. Let me do a show run, EIGRP, and we'll take a look at how our network statements are. Let me get rid of EIGRP. Always do that. There we go. All right. And let's go back and configure it. And I can actually come in here and say, do show. Oof. Seriously, Scott, come on. I can actually come in here and say, okay, actually, let me do my local ones this time. I can say, okay, I've got a 2.2 address on my Ethernet 1.0 interface, and I've got a 2.1 address on my loopback. This is as specific as you can get. You put in the network statement of the actual address on the interface with a wildcard or an inverse mask of quad zeros, meaning an exact match. It could be, what you choose to do. If you want to be as specific as possible, that is one of the options that you have, which means you're basically turning on EIGRP only on those interfaces. All right?
What's the difference between a local and connected?
A local route, the question was, what's the difference between a local route and a connected route? The connected route is the subnet that's connected to the interface. The local route is the address on the interface itself. So local routes are actually paired together with connected routes. You wouldn't see local routes without a connected route. So a local route is just the actual IP address that's on the interface. And then the connected route is the subnet that's attached to that particular interface. Make sense? All right. Now there's certainly another way that you can do this. You can be really lazy. Let me go ahead and get out of this screen here. You can be really lazy and you can say, okay, I just want to go ahead and enable EIGRP on every interface. So again, we're not running any other routing protocols. Router EIGRP 100. Network 0.0.0.0, 255, 255, 255, 255. You actually don't technically need the 255, 255, 255, 255, but basically what this does is it enables EIGRP on every interface and any interface that might be added even in the future. Okay. I don't recommend it, but certainly it's a very quick way of enabling EIGRP on every interface that exists on your platform. All right, it's one of those options that you have. Not recommended. Now, there is something else that I do want to mention about EIGRP. Even though it doesn't play a very significant role in EIGRP, it plays a much more significant role in OSPF and even potentially BGP. There's this thing called a router ID. All right. So if I come into my router here and I do a show IP protocols, now that I've got EIGRP enabled, you will notice that there was a router ID automatically selected in this particular case. The intent of having a router ID is to identify the router uniquely within the autonomous system. And in OSPF, it's the same thing. We're trying to identify the router within the autonomous system. But in OSPF, the router ID plays a much larger role into the process and the communication of OSPF than it does in EIGRP. All right. The way that a router ID is selected is 3 different steps, and you will need to know this for the exam, and it's good to know in general anyway. Router ID selection process, and this applies to OSPF, it applies to EIGRP, it applies to BGP. It works this way. Number 1, if you manually configure the router ID, that is going to take precedence over any other method. Usually this is done under the router process, but it depends on whether you're doing IPv4, IPv6, and so on. You have to manually configure the router ID. Number 2, if you haven't manually configured the router ID, it is going to become, it will be selected based on the highest active IP address on your loopback interfaces. Meaning that I'm going to take a look at all my loopback interfaces, and whichever one has the highest IP address, that becomes my router ID. In case you didn't notice, the router ID is a 32-bit dotted decimal number. All right. It does not have to be an IP address, but it does have to have that format. So naturally, it makes sense. I could choose one based on what's on my loopback interfaces. Number 3, it will be selected based on the highest active IP address on your physical interfaces. So clearly that's going to happen, right? I mean, you're a router, so you must have physical interfaces that allow you to do routing. Naturally, that's what you would typically see. All right. So this is the process again in OSPF, BGP, EIGRP. This is how the router ID is selected. Now we could specify the router ID if we chose. Our router ID was selected based on our loopback. 3.1 was our loopback interface. But I could go into the EIGRP process and say EIGRP router ID, and I put in the router ID in an IP address format. It does not have to be an IP address though. I could just simply make it 0.0.0.3 if I want, or I can make it 0.3.0.3, whatever I decide that I want to make my router ID. Okay. So we lose our adjacency, we get our adjacency back. That's because, by the way, that 15-second dead timer expired because of the router ID change. All right. Do show IP protocols, and sure enough, we can see that our router ID is now changed to 0.0.0.3. Okay. All right. We'll talk about a lot of this other stuff in here, all these other components of this output a little bit later on. The first step in verifying and troubleshooting EIGRP is to make sure that you have neighbors. All right? Because that is the first thing that has to happen in order for us to be able to exchange routing information. I have to have neighbors. The command that we use to verify that is show IP EIGRP neighbors. Well, guess what? The command that we use to do this verification in OSPF, show IP OSPF neighbors. In BGP, show BGP neighbors. Let me change something here real quick. Because my windows are going to be just way too messed up because the font size is so large. Let me change that to 12. Usually I'm projecting onto a screen, so I want to make it as big as possible, but obviously not in this case. So let me save that, apply that. Well, that's a little small. Okay, hold on one second. I thought it would still look okay. Let's go with a 16, should be good. There we go, that's better. All right, so there we go. Now I don't have the weird wrapping happening. Okay, so this is a really, really simple table to understand. Obviously, we should have one neighbor. In this case, our neighbor is 172.16.1.1. The H column is what we call the host index column. If I had multiple neighbors, that number would go from 0 to 1 to 2 to 3 to 4. And basically, it just represents the order that the neighbors were established. 0 being the first neighbor, 1 being the second neighbor, 2 being the third neighbor, and so on. All right. So that's one aspect of it. In this case, we only have one neighbor because there's only one link to another router. The address column shows the IP address of the EIGRP peer. That's the actual physical IP address on the interface that I've established the adjacency with. The interface column represents my exit interface, which identifies how I reach that particular peer. And then we have a hold time column. You'll notice here as I refresh, the values show IP EIGRP neighbors, goes to 12, goes to 10, goes back up to 14, 13, 12, 11, 10. It never goes below 10. And that's because this is a 1.544 megabits per second circuit, which means that my hello timer is 5 seconds by default and my dead timer is 15 seconds. So I should really never go below that 10-second threshold as long as I'm getting my packets. We'll talk more about the timers a little bit later on. Contrary to common belief, in EIGRP, the timers do not have to match in order for net routers to establish an adjacency, unlike OSPF, where the timers have to match. All right. The SRTT column, that stands for Smooth Round Trip Time. It's a value that's listed in milliseconds, as you can see there. And it basically defines how the router sends EIGRP packets to the neighbors and when that router expects to receive an acknowledgement for that particular packet. It's a way for RTP to measure the thresholds for the reliability mechanisms that are built into EIGRP. Again, this is what I was referring to when I was saying that RTP is not really a separate protocol. It's really just functions that are built into EIGRP. Well, this is one of those particular functions. Actually, both of those columns, SRTT and RTO. RTO stands for retransmission timeout, and that represents basically the amount of time that the router is going to wait before it sends a packet from the retransmission queue over to the neighbor, over to the destination. Remember, there are 3 packet types that get acknowledged in EIGRP: an update packet, a query packet, and a reply packet. So those 2 columns are used to identify that. The Q, or QCNT, Q count, that basically shows me how many packets that have been generated in software and they're waiting to be sent to the neighbor. You would never see any number but 0 here unless you were having some serious congestion issues in your network and the router CPU is spiked, or it can't process datagrams quickly enough, and so on. All right, and then a sequence number is exactly what it sounds like. notice that the sequence number isn't changing unless I change something about the router. So if I come in here to loopback 0 and do a shut and a no shut, that's going to trigger a reconvergence process. And if I now go back and look at my neighbor, you can see that the sequence number incremented. So there were some updates, there were some replies, updates and acknowledgments and so on that happened. So the sequence number increments each time transactions take place between EIGRP peers. All right. We can also use the detail option if we want to see specifics about that particular neighbor. So I could come in here and I could do add a detail option, and I can see still the same information here, but here's the number of retransmissions. Here's the number of prefixes that are being learned by the neighbor, which makes sense. Those are all the prefixes that are based on this topology: 1, 2, 3, 4, and 5, right? The connected routes don't count. This loopback is not connected. This Ethernet's not connected. This serial's not connected, and these two loopbacks are not connected. So prefixes is basically how many prefixes I'm learning from the neighbor, and so on. This is the software version, the EIGRP version that the neighbor's running. All right. So, which by the way does have to match, although it really never should match. I mean, unless you're running really, really old routers. Another command that you can use to verify EIGRP is to do a show IP EIGRP interfaces. The nice thing about this particular command is it gives you a very quick representation of which interfaces are actually running the protocol. And in this particular case, we can see that serial, it's a little bit wrapped around here, unfortunately, but serial 2.0 is running EIGRP, loopback 0 is running EIGRP. We can also see that we have one peer, one neighbor on this interface. What multicast pending, multicast and pending routes, that's kind of wrapped around here, but that's really not that critical. All right. It's not critical to understand the details of that. Like I said, you can use the detail option and on the show IP EIGRP neighbor command, but we also have a detail option on this one as well. Now, this is actually very useful because there's two things that you can glean from this particular configuration. What the timers are on the interface, whether or not split horizon is enabled or disabled, which is a very important concept within EIGRP, all distance vector routing protocols as a matter of fact. How many packets have been sent, how many hellos have been sent, how many unicast versus multicast packets. So you'll notice here that everything has essentially been done as a unicast packet. And that's an interesting concept as well. All right. And the reason why that's interesting is that we always get taught that EIGRP uses 224.0.0.10 to send out its information. It depends on the circuit type. In a broadcast domain, multicast tends to be used because then I can communicate to multiple routers at the same time. But on a point-to-point serial link, there's no need to use multicast because there's only two endpoints that potentially could be on that particular link. So in that particular case, EIGRP decides to use unicast. It might use multicast initially, but then it will convert, it'll change to unicast once it establishes the adjacency. All right, so a lot of good information in this particular output as well, just to do some additional troubleshooting as necessary. All right. One of the other commands that I showed you guys,
What was that command again? I missed it.
it is show IP, here, let me just scroll up, show IP EIGRP interface detail.
Oh, detail. Okay.
Yeah, we're just adding the detail option to the show IP EIGRP interface command. Now, another command that I've already actually used and shown you guys is the show IP protocols command. It's not specific to EIGRP protocols. That's right. Yeah. It's not specific to EIGRP, but it is a command that allows us to verify the operation of any routing protocol. Sorry. Something popped up on my screen. Any routing protocol, whether it's OSPF, whether it's EIGRP, whatever. Doesn't really matter. Okay? And we can use it even to verify just basic static routing and whatnot. So we're seeing here that we're running EIGRP in Autonomous System 100. These are the metric weights, which we call the K values, that happen to correspond to components of the metric itself. We'll get into that a little bit later on. The defaults are K1 and K3 are 1. The rest of them are 0, which should never change, right? You should never change the K values. We can see the router ID for this particular router, 192.168.1.1. The administrative distance of the protocol, internal is 90, external is 170. By the way, an external EIGRP route is just any route that's being redistributed into EIGRP. Maximum path of 4, which indicates how many equal cost paths I'm going to load balance over. By default in IPv4, all of our protocols do 4 by default, with the exception of BGP. BGP doesn't do load balancing. Maximum hop count 100, so that's the diameter of our EIGRP domain. And then a variance allows us to identify whether or not we're doing equal cost or unequal cost load balancing. All right? So we will talk about that later. That's a very important concept, but I don't want to get sidetracked right now because we have a whole discussion on path manipulation and path selection, which both of these values are related to. All right? Automatic network summarization is disabled. Very important concept. In the case of, because you will see this in the troubleshooting test, and if you do happen to go take your CCNA exam, if you haven't taken it, you'll probably see it on there as well. Cisco used to have a command under the EIGRP process. Let's try to get rid of that. Mistake. That was called auto-summary. And they've removed it from 12 something and beyond. They got rid of it by default. But what auto-summary does is it says, go ahead and, even though this is a classless routing protocol, let's go ahead and make it act classfully. So now I can see that automatic network summarization is enabled, and I'm summarizing 3 components with this metric, and we'll get into summarization later on, but basically I'm just advertising classful networks now. I'm no longer advertising the individual subnet. If you look at the topology, I'm on BR1, 192.160. Well, unfortunately, I'm not going to be able to see the effect of it because this is already a classful subnet. But what I was going to try to demonstrate was the concept that now I'm summarizing all of my networks into their classful, major classful boundaries. Bottom line, you don't ever want to run that because it's not really conducive to a modern network design because we have subnets all over the place. And to summarize all of my 10 subnets as 10.0.0.0 could be highly detrimental to what you're trying to accomplish in your network. All right? So we always want to make sure that that's turned off. All right? Then routing for networks. Essentially, this defines basically how my network statements were entered. We used a wildcard mask on this one, 0.0.0.3, which was an inverse mask of /30, and we didn't put a mask on our 192.168.1.0 network because it was already classful. Okay. Finally, my routing information sources, which is basically my neighbors. I got an update from that neighbor 25 seconds ago. That's because I switched from auto summary to no auto summary. and then this is the IP address of that particular neighbor. So again, it's not that these commands are complicated or that they're difficult to understand necessarily, because they're really not. It's just a matter of logically thinking about the process. What has to happen before the next thing can happen? And that's really the biggest takeaway that you guys can have from all of these discussions, is the logic of everything. Neighbors first, then topology, then routing. Well, okay, troubleshoot neighbor relationships. If I don't have neighbors, then I can start to whittle down all of the different options to verify the neighbor relationship, to identify what the potential issues are with that neighbor, and so on. Does that make sense? So it's more about understanding the logic and just understanding the progression that we go through to make things work successfully. All right, let's go into our HQ router now. And let's see, where is it at? Right here. Okay. And we're going to do a couple of verifications on this router as well. Show IP EIGRP interface. Now, in this particular case, we should see some significant differences here. Let me change the settings on this one as well. I think I chose 16. Yeah. All right. So we can see that in this case, obviously, we're running EIGRP on several different interfaces: Ethernet 1.0, Serial 2.0, Serial 2.1, and Loopback 0. The key here is that, well, actually, before I even get into that, let's just assume that the loopback interfaces represent LANs. All right? Meaning that they represent subnets that have hosts connected to them. We typically do that in lab environments in GNS3 just to simulate subnets that we're trying to generate and distribute through our routing process, or any lab that we might have any kind of routing process. So let's assume that Loopback 0 is not Loopback 0, but it's an Ethernet network that has clients connected to it. The bottom line, though, is that I don't need to be running EIGRP on that interface technically, because there's no routers there that I'm intending to exchange information with. All right. So let me go to the diagram and explain what I mean by that. So I've got all these loopback interfaces.
I got a quick question. Now, that would be totally different for OSPF, but you would probably want to advertise that loopback for.
Well, okay. So whether you decide, whether you decide to advertise your loopbacks or not, it just depends on whether or not you want to use those loopbacks for management purposes or for other reasons, right? To manage a device and whatnot. My point in this case, go ahead.
Well, my question is it more important in OSPF to do that, or maybe not important, but more common, I guess?
Well, it is very common in any case to have loopbacks for lots of processes. Because the reason we tend to use loopbacks even outside of OSPF is because they don't go down, right? There's no physical layer tie-in to a loopback. So unless it's shut down or unless the router fails for some reason, loopback interfaces are always up, which means that they're great interfaces to do troubleshooting with. They're great interfaces to tie in management components. We use them to tie in or bind NTP messages. We use them to bind.
I understand that, but my question was, it's not really any more important than between EIGRP and OSPF to have that loopback.
Correct. Right.
Okay.
Okay. The use is the same in both cases. You don't have to have loopbacks for OSPF to work. You don't have to have loopbacks for EIGRP to work. Now, the point that I'm trying to make in this particular case is that these loopback interfaces are here to simulate networks. And that goes into the next discussion that I'm trying to get to here, which is that let's assume that this is a network that has clients connected to it. Rather than a loopback, it's some sort of LAN, and we've got hundreds of clients back here. We don't want to send EIGRP hello packets out this interface. Somebody can capture that hello information, and then based on that hello information, they can identify things about our EIGRP domain that we may not want to be public knowledge. So we need to suppress the hello packets from going out of that interface so somebody can't throw in a rogue router and connect to our domain. And we don't want to waste bandwidth. And the way that we do that is we use a passive interface option. Let me, I keep forgetting to scroll through some of these slides here. So there's our neighbors, our interface command, our show IP protocols command. So this is where we're at. We're talking about passive interface. Passive interface works exactly the same way for RIP, OSPF, EIGRP. It suppresses the protocol from running on the particular interface. Now in RIP, it's a little bit different because in RIP, we don't form neighbor adjacencies. So passive interface does not suppress the receiving of routes, but it suppresses the sending of routes in RIP. In OSPF and EIGRP, passive interface suppresses both because I only exchange routing information with my neighbors. And if the interface is passive, I'm not sending hellos and I'm not accepting hellos, which means I can't form a neighborship with a router, which means I'm not going to be sending updates out that particular interface. Now there's a couple of ways that you can implement passive interface. Let's say we're back in our HQ router here. We want to make sure that loopback 0 is passive, but these serials and the Ethernet 1.0 interface are not passive. Now there's a couple ways I could do this. I could come into EIGRP 100 and I could simply say passive interface default, which makes every interface passive. All right, notice I lost all of my neighbor adjacencies. And then I can do no passive interface serial, let's see, 2/1, no passive interface serial 2/0, no passive interface Ethernet 1/0. Not a very effective way of doing this, but my point is that you can make interfaces passive or you can make them not passive. Let me just show you what the commands look like all together. Oops. All right, so that's what those are the commands that I entered. Now, it would have been much more effective just to simply make the loopback interface passive and leave the rest the same. By the way, troubleshooting ticket on the troubleshooting test has to do with passive interface being turned on. Just FYI, that troubleshooting test is it's challenging, but the tickets themselves are not really complicated. They just put so much junk into that test that it just makes it hard to find, to find what you're looking for. But the actual tickets themselves are not extremely complex, right? They're not throwing in some obscure issue. It's they're turning off interfaces or doing something passive like that, doing passive interface or something like that.
So this approach right here would really be the more secure approach, right? Because you have to actually explicitly define the interface if you want that traffic.
That's a great point. You could say that my standard practice is to do passive interface default, which forces me then to make interfaces that I explicitly want to allow EIGRP, not passive. Yeah, it's a great point. It could be just another kind of a best practice way of looking at it, right? It just requires that you know what you're doing and you know that that you're going to explicitly allow and then implicitly deny. Although it's not implicit, it's something you configure, but yeah, absolutely. Okay. Show IP protocols. Again, will show us information. We can see in this particular case now, loopback 0 is passive in this case, and so on. All right. Now, we'll go ahead and leave that. What we're going to do now is we're going to do a couple of debugs. We're going to take a look at the hello process and how often hellos are sent and received. You know, and do some basic debugs. On the troubleshooting test, you don't get an option to do debugs. You can do basic show commands. But in the case of real world, we obviously want to be able to you know, do debugs to see something happening on a regular basis. So we're going to go into BR1 in this case, and we're going to run really one of the most common debugs, which is debugging the hellos. Debug EIGRP packets hello. By the way, there's two things that you can do with debugs in EIGRP, and I ran into this way back in the day when I was first learning how to configure EIGRP. You can debug the IP protocol stack for EIGRP, and you'll notice that I don't have the option for like hellos, updates, queries, replies. So the debug IP EIGRP commands relate directly to debugging the IP implementation of EIGRP, whereas debug EIGRP is more debugging the actual protocol itself, right? Neighbors, packets, transmit timers, and so on. So it depends on what your overall objective is with the debugs. But just note that there's two different ways you can do debugs in EIGRP. You can use the IP option, which gives you a whole bunch of different debugs than without the IP option. So in this case, we're going to debug EIGRP packets. And you can see here that we have several different options, right? Stuck in active query, stuck in active reply, acknowledgement, hello, query, reply, request, retry, stub, terse, and update. Of course, we're going to learn all about stub routing a little bit later on. And we'll talk about what queries are and what replies are and what stuck in active is and so on. But in our particular case, we're just going to start by at the ground level, just simply debugging our hello packets. All right. Now, in GNS3, we're simulating a console connection. But if I was doing this over a V2Y session, SSH or Telnet, I'd have to do a terminal monitor to see these debug outputs. But basically, if you look at the timestamps there, you can simply you can see exactly how often we're receiving those hello packets from particular neighbors. In this case, they're all coming from one neighbor. Let me do an undebug all and get rid of that. Hold on one second. All right, and we can see that in this particular case, we're getting hello packets every 5 seconds, right? Well, we're seeing the sent and receive. We're not synchronized here, but here's 37, 42, 47, and so on. So we have to look at the received 37, 42, 47. So every 5 seconds, we're getting that hello packet. All right, we're also sending it every 5 seconds. Obviously, this is what this is the important concept in establishing these adjacencies. But you may decide that you want to modify those timers. Remember, I told you that the dead timer is 3 times in EIGRP. You can independently configure the timers in EIGRP. They don't have to. They don't have to match. The timers don't have to match, right? They don't have to be 3 times. You can make it 4 times, 5 times, whatever you decide you want to make. There's pluses and minuses to changing the timers. Obviously, the longer the timer periods, the less traffic is going to be generated. But the longer the timer periods, means that essentially the longer it takes to identify failures and to converge. So 5 and 15 seconds on our high-speed links, 60 seconds on NBMA networks or links that have a speed of lower than a T1 speed, so 1.544 megabits per second. Hello packets, obviously, we know what they're used for. They're used to obviously identify neighbor relationships and maintain neighbor relationships and so on. We already looked at this command. If I come back into my HQ router here and I do a show IP EIGRP interface detail, I can see what my default timers are, 5 and 15 seconds. And I can adjust those values if I want to. All right. So we already looked at the hello packets on the router. And what we can do is we can shut down an interface. And I'm not going to do it in this particular case. They do it in the book, but I'm not going to do it. They just want to demonstrate the idea that by shutting down an interface, I will lose an adjacency with my neighbor based on the dead timer expiration. Okay? Let me point something out here, because I think this is also an important concept to understand. If I went into BR1 in this case, and I shut down the serial 2.0 interface on this router, okay? If I shut down the 2.0 interface on this router, then obviously the neighbor relationship would immediately disappear, because the link status on this interface goes down. HQ is smart enough to say, well, my data link layer and my physical layer are down, so that means that I can't have a neighbor on that interface. But what about the case of frame relay? If I shut down the 2.0 interface on BR3, because HQ is connected to a cloud, essentially, service provider network, the link status of the interface on this side does not affect the link status on this side. So in this case, we would only be able to identify that the neighborship went down based on the dead timer expiring. And that's really what they wanted to demonstrate, was that concept that, hey, if I shut this down, then it's going to take, you know, our hold down timer is going to expire and we're going to lose our neighbor relationship. All right? All right.
An access list on that top router would be the same thing.
Exactly. You could throw in an access list to block inbound EIGRP. You can't set up an access list to block outbound, because access lists can never filter traffic coming from the router itself. But you know, you could do inbound. All right. So we can manipulate these timers if we decide that we want to, and this is done on a per interface basis. We can see the commands here. Let me switch over. These are all the things that we already did, the debug and everything. But we can, and then this is the shutdown that I was mentioning, where they wanted to show you that the hold down timer expires on the interface and so on. We're not skipping anything here. This is all stuff that we looked at in the actual command line. But you know, we can manipulate our timers if we choose on a per interface basis. Now, here's the interesting thing about the timers themselves, because there's a misconception typically about how the timers work in EIGRP. So they want us to go into BR3 and adjust the hello timer to 10 seconds and the hold timer to 30 seconds. So let's go ahead and do that. BR3, which I believe is this guy right here. Yep. Show IP route, pipe include connect. So serial 2.0. And we're going to do a IP hello interval and EIGRP 100. And let's just make it 10 seconds. And then we'll also do our IP hold. time and EIGRP 100, and we'll make it 50 seconds because it doesn't have to be 3 times. I know in the book they have it 3 times, but it doesn't have to be 3 times. Now you'll notice that I did not lose my neighbor relationship with the other router. All right. I guess it didn't change the settings for every window. I changed the default settings so in the future as we, oops, I didn't choose the right one. As we open up tabs in the future, they'll automatically be the new setting. But let me change this to 16 real quick. All right. So I changed the timer, but I did not lose my neighbor relationship. All right. Now, if I do a show IP EIGRP interfaces detail, I can see that the timers have been changed based on the configuration that I applied on the interface, which is interesting because now HQ has a dead interval. Actually, let me even make this worse. Let me come in here to interface serial 20 and change the IP hello timer to 20 seconds. All right. Now, that means that I've extended the hello timer on this router beyond the dead timer that's configured on the HQ router. The dead timer on the HQ router is 15 seconds. The hello timer on this router is 20 seconds. But the dead timer on this router is 50 seconds. And the dead timer on the HQ router is 15 seconds. So we got all kinds of weird things going on where the timers don't match and my hello timer now exceeds the dead timer of the other router, but I haven't lost my adjacency. Show IP EIGRP neighbor, and I've certainly been talking for more than 15 seconds. That's because the timers get negotiated. All right. Again, show IP EIGRP interface detail, and I can see that my timer is 20 and 15 seconds. Now, if I go to my HQ router, and let me do a show CDP neighbors. Oh, I'm not running on BR3 frame relay. Doesn't work very well. Let me just look at my diagram here. So it's serial 20. So if I do a show IP EIGRP interface detail on this case, you can see that for serial 20, the hello, oh, never mind. It's an NBMA network, but the point is still valid here. It's just the opposite direction now. I forgot this is our frame relay circuit, which is NBMA, and remember the timers on an NBMA circuit are 60 and 180. All right, but still the same concept applies. The hello interval on HQ for this circuit is well beyond what the dead interval is on BR3, which I set to 50 seconds. So what's happening in this case, right? What's happening in this case? Well, if I do a show IP EIGRP neighbors, you can see here that I go down to 33. Remember, we're looking at serial 20 in this case. That's that is the link that goes to BR3. Lost my train of thought there for a second. You'll notice that even though my timer is set, hold on one second. Sorry, dog was barking. You'll notice that even though my timer is set to 60 and 180, if you take a look at what the actual values are, 37, 37, 36, 35, 34, 33, and then it goes up to 50. So what happened in this case? What happened in this case? They negotiated the dead interval, right? They negotiated to the 50 seconds. So even though the serial interface, show IP EIGRP interface detail, even though the serial interface for 2.0 is set to 60 and 180, it negotiated the timers based on what BR3 was advertising. So in the case of EIGRP, the timers don't have to match. They simply get negotiated between the two routers. Okay?
So I guess it uses the less value of the two?
In this, yes, it uses the less value, the smaller value in this particular case. All right? Now, it is possible that you could see some issues. They don't need to be identical, but there may be, obviously, whenever there's a negotiation of something, it is possible that that negotiation could fail or something could happen within that negotiation process. So it is not really a good practice to make your timers different. But unlike OSPF, where the timers absolutely have to match, in EIGRP they get negotiated. All right? Yes?
But now, so we've been using BFD a little bit lately, and I was just curious, is now a good time to maybe talk about the comparison of this versus BFD?
I can mention it briefly. We are going to see BFD a little bit later on when we get into some of the enhanced features, but BFD is a secondary protocol that you can run on these routers that decreases the amount of convergence time for lost neighbors and neighbor discovery to a sub-second value. I don't want to get into the specifics of the protocol right now because we will talk about it a little bit later, but that is really the modern approach to managing neighbor relationships, is to use the BFD process, which is, again, it's not tied to the protocol specifically, but it's incorporated into the use of the protocol as a separate function to ensure sub-second convergence between neighbors and if neighbor relationships change and so on. It allows us to augment or supplement the standard timer processes that exist with these different routing protocols. I can kind of give you guys a little bit of information, right? A little bit of background on this, but I'm just trying to think about how much detail I want to get into it. What he's referring to. Yeah, go ahead. No. Let me at least do like a quick introduction because some of the folks may not be aware of what BFD does, but it's a separate protocol. It's not incorporated into EIGRP or OSPF or ISIS, but BFD stands for bidirectional forwarding detection. All right, and the whole point of BFD is to detect some sort of issue or some sort of fault between forwarding engines, routing protocols in this particular case, over a particular link. All right, so it is relatively benign. The protocol itself, it doesn't add a whole lot of overhead. And it provides for fault detection even on links that don't support failure detection, like virtual circuits or MPLS switched paths and so on. Essentially what happens is two routers form a BFD session between the two endpoints over whatever link that you've configured it on. And you can do multiple BFD sessions if you have more than one link between the different routers. And then those two routers then form a three-way handshake. They go through a three-way handshake process, almost like a SYN-ACK process, to establish that they have this bidirectional forwarding enabled. All right, and you can even add authentication to the process as well, using simple password authentication or MD5 or SHA-1. There is no automatic discovery for BFD sessions, so you can't just simply turn it on and then it goes out and tries to discover all the neighbors. You have to explicitly configure BFD between your endpoints. But essentially, the protocol itself is there to manage adjacencies between OSPF or EIGRP and so on. And some of the protocols, it's actually starting to be built in. Like I said, later on we're going to have a discussion about BFD. We'll have a lesson about BFD. So I think so far I've kind of introduced the concept, and I think that's enough for now. But thank you for bringing that up. It's a very, it's definitely a modern approach to implementing neighbor loss discovery and so on. It's a very important concept to understand. So thank you for bringing that up. And I will make sure, well, we're going to see it later anyway. So, all right, we'll see the configuration components and take a look at how it's actually set up. But it's called BFD, in case you guys weren't aware of it previously. All right, so we got a couple more slides in this lesson here, and then we will continue on. All right, frame relay. Now, frame relay is kind of a unique monster because it is considered to be NBMA, non-broadcast multi-access, and because it is traditionally non-broadcast, or it has been in the past, it means that multicast establishment of neighborships is not possible. Now, here's the thing about frame relay. If I do a show frame relay map, not show frame relay map, you can see that in this particular case, I've got my frame relay connection on serial 20. This is the local data link connection identifier and the hexadecimal version of the hexadecimal value for that. But you can see here it says broadcast, right? So even though technically frame relay is NBMA, non-broadcast multi-access, it actually does support broadcasting. It does pseudo broadcasting. So even though frame relay has traditionally been defined as a non-broadcast type of circuit, it actually technically does support broadcasting. It's up to the service provider as to whether or not they're going to actually support broadcasting over the frame relay network, but as a technology, it does support broadcasting. So you have to identify whether or not your frame relay circuit supports broadcasts or not. Then you can identify whether you can do automatic neighbor discovery and so on. We also talked about the concept of split horizon, right? If you have a point to multi-point frame relay topology, on the multi-point side, you're going to have an issue with split horizon, meaning I'm never going to advertise a route out the same interface that I receive it on. So your best bet in the case of a distance vector protocol with frame relay, because remember, link state protocols don't use split horizon. They don't need it because they have a complete picture of the topology. So they know whether or not there's a loop in the topology. Whereas distance vector protocols, because they don't have a complete picture of the topology, they have to have functions built into them that allow us to manage things like loop avoidance or to have loop avoidance mechanisms built in, and split horizon is one of those mechanisms. All right. So that's a consideration. If I want to run frame relay over, EIGRP over MPLS, well, it's obviously going to change depending on whether or not I'm establishing a layer 3 MPLS VPN or whether I'm establishing a layer 2 MPLS VPN. Layer 2 MPLS is pretty basic. It essentially is a layer 2 broadcast domain. So establishing neighbor adjacencies, it supports multicast, it supports broadcast, it supports unicast. So there's no real issue over a layer 2 MPLS VPN. In a layer 3 MPLS VPN, you need to decide where you're going to run EIGRP. Am I going to run EIGRP just back inside my network? And then I'm going to redistribute those EIGRP routes into the PE router by using some other protocol like BGP or OSPF or whatever between the PE on the PECE link, or am I going to run EIGRP natively all the way up to the PE router? just something to consider because, and here's the biggest consideration, if I'm redistributing routes in and out of another protocol, the administrative distance of those routes is going to change. They become DEX routes instead of D routes, which may or may not be a big deal. It just depends on how routes are being established, right? So that's an important, very important concept to understand, whether or not they're going to be DEX routes or D routes and so on. You have to be aware of that, all right? As far as the actual routing goes, though, there really isn't a limitation about disseminating routing information across a layer 3 MPLS backbone, because whatever routes are here, they get redistributed into your PECE link protocol, and then they go into the VRF, and we use MPBGP to exchange routes over the MPLS backbone, and then they get redistributed back into the IGP in your at the other side of the network. All right, metrics can be maintained. The only difference is that the service provider is participating in that routing process. All right. When it comes to a layer 2 MPLS VPN, not a whole lot to consider in that particular case because it's basically just a big switch in the middle. It's like almost like a metropolitan Ethernet network where you're running either a point-to-point VPLS, VPWS, virtually private wired service, or you're running what this diagram depicts, which is basically a layer 2 broadcast domain, which is a VPLS, virtually private LAN service, which is pretty common in the case of MPLS. All right, the considerations here are not nearly as complex. Routers will form adjacencies with each other. They'll share routing information. We don't have to worry about redistributing routes into a secondary protocol and then exchanging those routes across the network and so on. All right. All righty. So that concludes that lesson. And I think we got a lot of good stuff in that lesson. We're going to go into the second lesson, which is building the EIGRP topology table. Really, really important concept here. And we're going to talk about what that topology table is. How do we decide what the best path is in a network? We're going to talk about the EIGRP metric. We'll talk about how EIGRP routers share routing information and so on. So we'll see you guys in the next lesson.